Thank you, everybody, for coming to our talk. Hopefully, you'll learn something today. So, as the intro said, I'm a production engineer. That means that I'm around when all the stuff in production starts blowing up. And that means that things like overload protection are very important to me. And I was very thankful that I had Sean around because he wrote this fantastic actor framework that we're going to be talking about. I know what you're thinking, yet another actor framework. But this one's really good, trust me. For real this time. And that really saved our bacon multiple times, or saved our crab meat. I don't know, that's kind of macabre. So let's get right into it. So today what we're going to be talking about is that I'm going to go a little bit into the motivation for why we're doing things in this particular way, which has to do a lot with the history of Rust at Meta/Facebook. I'm going to talk a little bit about how we use Thrift internally for like RPC stuff. I'm going to talk about like how Rust Thrift servers work. And I'm going to talk, finally, we're going to talk about like why did we choose actors? How did we use the Ractor framework to do actor-based stuff? And like all the internals of that, factories and overload protection. And then we'll put it all together and explain how we ended up solving the actual business problem. So I'm just going to start talking about like how Rust came to be at Meta/Facebook. So the first serious usage of Rust started around 2017-ish, right around the time I started, with this thing called Mononoke in the source control team. Basically, we were using Mercurial, and it wasn't scaling very well in our giant monorepo, and we were like, okay, we got to do something better. So Mononoke came along. Now, that was a very risky project, but it paid off, and it's open source. Rust was disadvantaged at the time because the interoperability between all the existing C++ code was not great. We had no CXX back then. That's dtolnace crate. That is really great. We only had bindgen, and that was like CXX at home. But it only worked with C-based stuff. So we had to like write C FFIs that on top of C++. It was a nightmare. So how did we try to drive more Rust adoption in that environment? Well, the nice thing about how our backend systems are structured is that they were mostly written in C++ or Python, but they were all exposing an interface over something called FB Thrift. If you're familiar with Apache Thrift, it's very similar. It provides an RPC framework and an IDL. We use it a lot in many of our services, like Scribe, for instance, which is our buffer distributed queuing solution, and ZippyDB, which is our distributed key value store. So the idea we had was, hey, what if we add FB Thrift support for Rust? And then we can leverage all the nice language agnostic stuff and build like our service mesh and clients using minimal effort. But there was a problem, which many of you I'm sure have run into, which is like there was a lot of middleware, there were a lot of features that were added and in response to real infrastructure needs like back pressure and overload protection, and they were only ever implemented as C++ server middleware. So it's like, okay, kind of chicken and egg problem. So the idea that we had was like, okay, bindgen is painful, CXX less so. So let's just try doing the bare minimum of FFI glue so that we can offload most of the work to the existing C++ FB Thrift server. We still needed to do some code gen using Mustache. I think it was Mustache, yeah. And we reused all the templating stuff and the FB Thrift compiler. And as you know, we thought that if we did this, new features that were added in the C++ side, we would just kind of get them for free and should just work for Rust FB Thrift servers. So how do we actually end up doing this integration? Well, so as I alluded to, we write a shim layer. It's like the golden rule of computer science. You have a problem, add another layer of abstraction. That doesn't work, add another one, and so on and so forth. So the idea we had here was that the C++ code would handle actually serving traffic on the socket, using their own thread pools, their own event loops to do I/O, and then Rust would handle just the request deserialization and calling the quote-unquote user code, the business logic, by spawning tasks in the Tokyo runtime. So how do you actually bridge these runtimes? Because they're very different. and I'll explain why. So in C++ at Meta, we have a library called Folly, which implements like executors, futures, semi-futures, coroutines, all that stuff. And of course, we have our beloved Rust async. So on the C++ side, we have, again, like this weird mixture of different concurrency primitives. All the futures there start executing immediately, so they're like eager. And there's a lot of multiple thread pool executors. There's kind of a meme that like any non-trivial application in the company, when you start it up, it has like at least 15 different thread pools spawned by like 12 different libraries. It's kind of a nightmare. And all of it is built on top of libevent-based, event-based for I/O operations. I don't know if you're familiar with that, but I'm not going to explain it. Just that's what it is. In Rust side, we kind of hide the futures behind the async keyword, thankfully. Don't have to use futures crate anymore. But you still have to pull futures to make progress, which is different from C++, different enough that it causes problems. And of course, the runtimes like Tokyo manage and abstract the thread pools. You can do like spawn blocking versus spawn, but good luck messing with the actual threads themselves. And then, of course, as we all know and love, there's the MIO-based reactor for actually doing I/O operations. So how do we reconcile these two approaches and models? They're very different. They have different priorities, different levels of abstraction, different internals. How do we do all of it? I mean, you're probably guessing that there's like a really cool engineering solution that you can use that will make all of this really great. The solution is pass function objects between them and hope it works. And surprisingly enough, this is not just good, it's good enough. So how does the basic Rust Thrift service work using this kind of naive solution where we just mash these things together until they kind of work? Well, our service client mesh service router, which you can read about in the paper, sends a request, and that request goes to the C++ Thrift server. And then once that request gets processed by the shim, we spawn the processing in the Tokyo task, which then will run on like the blocking thread pool or the non-blocking or the runtime thread pool as necessary. There's only one problem. Tokyo is really great at spawning things very fast. And Tokyo tasks is basically an unbounded queue. You can see where this is going. We kind of explode everything. So as long as traffic to our Rust services was relatively reasonable and we had enough capacity, everything was good. But as soon as you threw too much traffic all of a sudden, or you had big spike, you'd end up screaming at the computer and just being very sad. So we thought there has to be a better way to do this, right? I'm sure every engineer has thought that. So we thought, okay, maybe let's look into actors, right? Is the actor model a good fit? So as you may or may not know, actors have been used in a lot of like large-scale distributed frameworks and workloads. They solve a lot of memory management headaches in some frameworks. I have Carl Hewitt's definition of actor here if you're not familiar with it. But it's used a lot, for instance, if you've ever used like Erlang or Elixir, like WhatsApp. Did a lot of stuff using like actors or actor-like frameworks, and it generally works pretty well. Actors give you a couple of advantages over traditional like processing models because you can have really good isolation. The concurrent operations can all run within the thread pool. You have really good fault tolerance because you can handle failures in individual actors and have supervisors that prevent it from blowing up the entire system, as long as you're in a memory-safe language. You have a lot of, it's really easy to scale both horizontally and vertically using actors as long as your resources are properly allocated. And the state management becomes a lot simpler. You end up not having to have like a bunch of like, well, it used to be one cell, but now I think it's like lazy lock or something. We have a lot of like Folly singletons in the C++ world that make people very sad. But with actors, you don't need to really touch that at all. So I'm now going to hand it off to my dear friend Sean, who's going to explain how we fixed all of the problems that come with using actors with this new framework, Ractor. Thank you, Sean.
Thank you, Pedro. So A little bit of background on me. I work at Core Systems alongside Pedro as a software engineer, but my background is from WhatsApp at Meta. I've only been at Core Systems now for 6 months, about, but Erlang was our bread and butter. At the end of this, there was a talk that we internally call The Talk about scaling Erlang to 1 million connections per host. I highly recommend watching it if you haven't already. It's on YouTube. But we're going to kind of try and mimic some of that behavior that has been tried and true, tested in WhatsApp in these types of frameworks for Rust. So why a new framework? These sort of like float in an animated version, but there's a lot of them out there. There's Actix, Riker, Bastion, Alice's wonderful post about writing actors with Tokyo, which was quite inspiring actually for this work. But also there's a Reddit link that is probably 5 times longer than that screenshot with actor-like frameworks. The problem we ran into is they're either dead or unsupported. They've customized a lot of workflows away from true Erlang principles. They may not be flexible enough for what we were trying to solve. And one big painful one is that a lot of them run on their own runtime, to the point that like Actix is pretty much recommended not to mix with Tokyo at all. So Ractor, and we tried to like solve these again. It seems a little counterintuitive, but we actually find that we found a really good. What's it all about? So we really tried to stick with Erlang principles. So we have an isolated actor process. You can have optional state in the actor. You have supervision, which is implemented through, so actors can monitor other actors and are required to respond in priority above user messages when a child actor has a failure or thing. There's remote procedure calls, timers, named registry process groups. And the reason the last one is starred is this is actually not part of Erlang. This is from WhatsApp. In the talk, there's an introduction of factories and industries. And we've kept factory requires network connectivity, which we've solved to an extent, but with Thrift, we didn't really tackle it. So we got to factories and industries coming, I just need more time. So what are factories? They are not a factory method. Is usually the misconception that when every time I give this talk internally or something about it, everyone's like, oh my God, I hate Java. Please don't write a factory method ever again. And I was like, no. Very different. So what happens if a single actor, which is effectively a single message processing loop, can't keep up with the influx? You need to scale. How do you scale actors? That's work distribution. So a factory manages workers. They're both actors. In the diagram on the right, the little factory logo and each worker is an actor. I think my battery's died, I don't know, okay. The factory itself is only responsible for message routing. So it's very, very, very fast. And we have yet to be able to tip it over for influx of messages, processing the routing to workers. What happens if a worker fails? So this is where supervision comes in. The factory is created to automatically manage that failure state for you. So worker number 2 died. There's supposed to be an animation, but worker 1, like the one at the top, would be spawned in its replacement. So you lose the individual job that was being processed. The caller might be waiting on a result. They'll get an error because the channel that they're waiting to get the reply back will have been dropped, which is actually something I absolutely love about Tokyo channels, because in Erlang, you're just like waiting forever. And if you don't put a timeout, good luck. You're deadlocked. So yeah, anyways, the replacement worker will come up and the factory is managing the routing. So he'll just say worker number 2 was replaced. There's a new worker number 2 who can take work. This is also really important if you do some kind of funky stuff like shelling to Python, where the Python process, maybe you'd have 1 per worker and they can fail or crash because you were doing some oddball AI routine or something. You can spawn up a new process, and these are very expensive, so you don't want to be spawning them regularly. We're essentially keeping them warm by having workers around. Also, the factory is responsible for queuing. So every actor at its primitive has an unbounded message queue. This is an Erlang principle. If you want to put in a message queue, you have to build it and front it yourself. The factory is doing that. So if all the workers are busy, messages can queue up in the factory layer. And when a worker is free and says, I'm done, the factory routes another message. Now we're starting to see how we could maybe combine these together to make an overload protection and queue management solution. So what happens if the queue fills up? We can make it unbounded if we want, or we can make it bounded. If it's bounded, we can start rejecting when we start overflowing. And this is the principle of overload protection at Meta. There's also something called queue timeouts. If they sit in the queue too long, we scan the queue and flush items that have expired. But both of those result in a rejection. And in Service Router, which is our client service mesh, the user who actually made the call doesn't even see an error. It will automatically get retried up to a certain number of times. So the host is just, I'm overloaded, try it somewhere else. Service Router handles all that for you, and the caller doesn't even know. We'll just balance the work. If you fail X number of times, which is configurable, then eventually you'll be like, the whole tier is overloaded, figure it out, or back off or something. So that's how we would combine it all together. What do you do to bring factories into these Thrift servers? Well, we look back to the kind of diagram we had before. We no longer have unbound tasks where C++ would accept sockets as fast as it could, and we were just spawning a task as fast as we could. So that's great if the tasks end before new stuff comes in. In this case, they go into the factory, which has like this kind of routing logic, and either they get dispatched immediately if there's a free worker, or they can go into the queue, or get load shed. If they get load shed, C++ is responsible for replying back over the I/O socket with a special header code that says, like, this is a load shed event, service router retry and do all the service mesh logic and stuff like that. So this allowed us to solve that problem without having to rely on some more complicated underlying C++ logic. And the neat thing is we have two knobs now. The number of workers that you want, so concurrency, and the queue depth. We're going to talk about like how you kind of configure those two. So queue depth is the first one. Jobs sitting in this queue, in this case Thrift, control message latency. They're not yet executed. So we've constructed a future, but we haven't yet polled it. That's the job that's sitting in the queue. So the longer they sit, we're increasing processing delays. If the workers are all busy and the server isn't rejecting because like it's out of CPU memory or whatever, you still might want that job to be executed somewhere else where there's free workers. So this is a form of overload protection. In this case, you actually can tie it to a metric that the factory will automatically check periodically for you and can shrink or grow your queue based on whatever metrics you want to target. So if you want to say like, I want message latency and I want to target this latency, oh, I'm over that latency, let's shrink the queue down so I start rejecting faster to other nodes in my environment. Similarly, we can control the concurrency at runtime. The beauty of a factory is if I spawn or kill workers, they are done not in parallel with message processing. So if I'm going to check, am I overloaded with CPU, memory, network, or underloaded, I need to add more workers. That is an event factory processing state loop. So we're not processing messages as we add more workers, then we add the next message, and our worker pool is available. You can target up and down, and whatever combination of metrics you use. Internally, we have some like helpers for this off our deployment environment, but you can tie this to whatever you want. It's just a trait. Love that phrase. Now, request draining is also an interesting concept. What happens if your CI/CD pipeline decides, I'm going to update this host, and there are 15 long-running connections pending? Well, Prince Harry drops that connection on the floor, and they get an interruption. They have to now retry the entire thing. Normally, what we would do is we would send like a SIG abort, SIG term, yeah, and give a certain amount of time to drain host. With our existing implementation, we couldn't do anything about draining. We just had a massive amount of spawned off tasks, and we prayed that they were completed. But this is the lifecycle state of a factory. So when you spawn, you move into a started state. You can inject into any of these states custom logic. So I want to start up a bunch of resources, open database connections, whatever. Then I move to my factory processing loop, and that's just process messages as they come in, deal with scale events, stuff like that. Now, though, I'm going to say drain, and I'm moving from green to pink. In this case, I've sent that signal like, I got a SIG term, let's start shutting down. All new jobs will be rejected with a load shed event. In our case, we've tied that up, but really it's just a trait you implement, like on job rejected. And you can say like what to do with it. We say to send back a header code, but you can tie whatever you want to it. But let the queued jobs finish. Similarly, you can schedule a kill so that it won't drain forever, and say, I'm going to give you 30 seconds to drain, otherwise then I'm going to abort them. And then on factory stopped, you can do any teardown. So pretty basic life cycle, but it's nice and concrete, and you guarantee never to have a race condition dealing with spawning or tearing down, message processing, anything like that because of the actor model. So in conclusion, Meta has a really heavy dependency for service-to-service communication on Thrift. For Rust to really grow in adoption at Meta, we had to solve this problem. Solving that problem meant solving all of the headaches that come along with it, not just send a message and happy path it works. We had to solve overload protection, load shedding, all those things. We already had standardized on Tokyo at this decision, so that already excluded a lot of actor frameworks out of there, so we built another thing on top of Tokyo to solve that, and then wired it up to process Thrift. And factories are letting us scale outside of our single task loop and really load up as we need. So here's a bunch of links. There's RustConf library. Facebook Thrift is open source, and our Rust, not all of our extensions, but a big chunk of them are also open source, so you can take a look. And the last piece is the talk, which I highly recommend anyone get a chance to watch. That's really quite interesting on how factories can be applied. Thank you very much.